Assalamualaikum to Doctor. Today, my group will present the analysis operation management of Proton Tanjong Malim. Looking at the timeline, Proton was officially established in 1983. The launch of the TGM plant in 2005 and the strategic partnership with Geely in 2017 became major catalysts for growth. Today, Proton was transformed into a highly advanced Industry 4.0 automotive manufacturer. Our study focused on analyzing operational practices using the PDCA cycle and lean manufacturing principles to significantly improve productivity, quality, and overall operational efficiency. Moving on to the executive summary, our core focus is identifying and eliminating operational downtime waste within the production line. This issue directly affects plant efficiency. To resolve these operational problems, we propose practical lean solutions. This includes implementing total productive maintenance (TPM) and optimizing workflows through cellular manufacturing. To ensure quality and consistency, performance monitoring is driven by visual SOPs and skill metrics, allowing us to evaluate the effectiveness of these solutions through measurable KPIs.
This slide presents downtime framework which identifies the 8 major types of waste in lean manufacturing. These include defects, overproduction, waiting time, non-utilized talent, transportation, inventory, motion, and extra processing. Among these 8 wastes, our analysis found that defects caused by inadequate employee training and transportation caused by poor plant layout are the two most critical operational issues at Proton. These problems have a direct impact on product quality, production efficiency, operating costs, and customer satisfaction. Therefore, our improvement plan focuses primarily on these two critical areas while acknowledging the existence of the other types of waste. Next is Ishikawa or fishbone diagram. This diagram shows the root cause analysis of defects. So the causes are categorized into 6 main factors: people, machine, method, material, measurement, and environment. Among these factors, the people category is identified as the primary contributor. Inadequate employee training, lack of experience, and poor understanding of standard operating procedures increase the likelihood of assembly errors and inconsistent product quality. Other contributing factors include incorrect machine settings, poor quality materials, inconsistent work methods, weak quality inspection, and an unsuitable working environment. Overall, the analysis indicates that the main root cause is inadequate employee training, which affects work quality and leads to higher defect rates. This is operation management tools, same as the fishbone diagram. This is 5 whys analysis to identify the root cause of transportation waste. The problem begins with excessive movement of materials during production. The first reason is that components must travel long distances between workstations. This happens because machines and storage areas are located far apart. The third why reveals that the plant layout is not optimized to support efficient production flow. Furthermore, layout reviews are not conducted regularly and continuous improvement activities are not systematically implemented. Therefore, the root cause is identified as poor plant layout, which results in unnecessary material movement, higher handling costs, and lower production efficiency. Next, we have the SMART analysis. Based on the root cause analysis, we develop SMART operational improvement targets for the two critical operational issues. For defects, the specific objective is to improve employee training to reduce product defects. The target is to reduce defects by 20% while achieving 95% SOP compliance. This can be achieved through regular technical and SOP training under Proton's Kaizen practices with the goal of improving product quality and reducing rework within 3 months. For transportation, the objective is to improve the plant layout and reduce unnecessary material movement. The target is to reduce transportation distance by 50% and material handling time by 20% by rearranging workstations and optimizing material flow. These improvements are expected to enhance production flow and reduce transportation waste within 6 months. Overall, These SMART targets provide clear, measurable, and achievable goals that support Proton's continuous improvement and operational excellence.
Moving on to the first phase of our education, which do total productive maintenance TPM launch. We identify that unplanned machine breakdowns and robot malfunction are major pain point on the line. When these unexpected stoppage occur, they create a waiting time for Proton workers, which directly drags down their overall operational efficiency. To tackle this, our action plan is twofold. First, we will introduce autonomous maintenance, where the operators themselves will perform basic cleaning and daily inspection before their shift start. Second, we will create simple daily checklists and track our machine efficiency using a visual OEE dashboard. By shifting our culture from reactive firefighting to proactive check, we ensure that the machine runs smoothly, effectively cutting down on idle line downtime. The second part of our education focuses on plant layout optimization and serial manufacturing. Currently, we are facing long moving distances for heavy parts like engine and panels. This messy optimized layout causes unnecessary transportation, extra movement, and ultimately lead to worker fatigue. Our solution is to rearrange the assembly line into a U-shaped sequence, also known as a cellular layout. Along with this, we will bring all necessary through parts and workstation much closer together. Shorter walking and moving distances directly eliminate transportation waste. By reducing physical strain, we keep our operators energetic and focused on throughout their shift. The final intervention in our implementation phase is the deployment of visual SOP and schematics. We noticed that a lack of proper training or overly complicated text heavy guidebooks frequently lead to assembly errors. This results in a high defect rate and forces the team to spend extra time on wasteful reworks. We plan to address this with two distinct steps. We will replace those heavy instructions with highly clear, visual or picture SOP placed right at the worker's eye level. We will implement a skill-metric board to visually map out or match the right skill worker to the right task on the line. Clear pictures and visual cue prevent workers from making accident mistakes. This standardized quality cuts down defect rates and completely eliminate wasteful rewards. To wrap up our execution phase, this slide displays our 3-month action plan and timeline summary. It showcases exactly how we will manage the timeline, PIC, cost, and our expected milestone. Month 1, we will kick off the TPM launch. This will be driven by the maintenance team and the line supervisor. The estimated cost is low as it only requires jelly spray out and it is expected to minimize sudden breakdowns and reduce idle waiting time. Month 2, we will shift our focus to the cellular layout workstation redesign. This will be headed by industrial engineering. The cost here is medium due to physical relocation expenses, but it will successfully shorten component transit distances and eliminate motion waste. Month 3, we will roll out the visual SOP and schematic. This requires a cross-functional effort from the operational manager, QA team, and the HR training session. The cost is low for printing guides and it will standardize assembly quality while lowering defect rates. In summary, this structured treatment timeline ensures that we implement this lean intervention systematically to achieve maximum operational impact with highly controlled costs.
So in this slide, I will explain the 4 KPI used to measure the success of the lean intervention at Proton how this work, right? Tanjong Malim. So the first one is the mechanical reliability index measure, machine stability after implementing total productive maintenance (TPM), and improvement in this KPI indicates fewer machine breakdowns and smoother production with production speed increased from 7 to 10 per hour. Second, the station cycle time consistency and ergonomic waste index evaluate how efficiently operator perform assembly tasks by placing tools and components closer to the workstation. Unnecessary movement is reduced, resulting in more consistent cycle time and improved productivity. So the third one, the first time right manufacturing rate and TBR, which is ticket barang rosak system law. The FTR rate measure the percentage of vehicle that successfully pass through the assembly line without requiring any rework or defect correction. This KPI evaluates how effective visual work, instruction, and standardized operating procedure are in reducing assembly error and preventing damage to high-value components.
At the same time, the TBR system record defective part report during production a higher first time rates and fewer TBR report indicate that assembly error and product defect have been successfully reduced. So the last one, the cross-functional capability score, measure the workforce flexibility. It tracks how many operators are trained to work at multiple stations, helping Proton maintain the production even during labor shortage. So in this slide, I will explain the procedure used to evaluate the effectiveness of lean intervention. So the step one, Proton established a historical baseline by collecting past operational data such as and equipment downtime and labor productivity. This provides a clear comparison between performance before and after the lean implementation. So the step two, the line supervisor conducts shift level operational verification twice a day to ensure the operator follows standardized work procedure and complete their pre-shift maintenance check. So the third one, the quality assurance department perform a weekly review of the ticket barang rosak TBR system. They monitor defective part, calculate quality costs, and ensure that standardized work instructions are reducing assembly error. So the fourth, the industrial technology department carry out a monthly time and motion studies to evaluate operator movement, workstation efficiency, and production line balance. This helps identify opportunity to further improve productivity. So the last step, after 3 months, the operation manager conducts various analyses. If performance targets are not achieved, corrective action are taken, such as providing additional dojo training, assigning experienced body trainer, or improving the supply chain process to eliminate production bottlenecks.
So next, I'll present to you about ACT, which is long-term follow-up actions. So for this ACT phase focuses on making sure the lean improvements are maintained over the long term. These follow-up actions help Proton continue improving its operations, maintain high product quality, and prepare for the future growth, especially with the increasing demand for electric vehicles, which is EV. Okay, so we'll go through by one. Okay, so for the first point, which is continuous improvement program, which is monthly review meetings and employee suggestion systems. Okay, so for this, Proton should organize monthly meetings to review productions, performance, and discuss any operational issues. Employees should also be encouraged to share ideas because they work directly on the production line and can suggest practical improvements. So next is continuous training and multi-skilling, which is regular technical training, update skill metrics, and employee training for multiple workstations. So for this, employees should receive regular training so they can improve their skills. So by updating the skill metrics and training workers to operate different workstations, Proton can reduce manpower shortages and increase workforce flexibility. So thirdly is digital maintenance and production monitoring, which is IoT sensors, real-time dashboards, and predictive maintenance. Okay, so for this, Proton should use digital technologies such as IoT sensors and real-time dashboards to monitor machine performance. So predictive maintenance helps identify machine problems before they become serious, reducing downtime and keeping production running smoothly. And for the fourth is production capacity layout review, which is annual capacity planning and expand facilities when needed. So as customer demand, especially for EVs, continue to grow, Proton should review its production capacity every year. If needed, the company can expand its factory or redesign the layout to improve production efficiency. And lastly is strengthen supply chain coordination, which is strong supply collaboration and digital inventory tracking. So for this, Proton should work closely with suppliers and monitor inventory digitally. This ensures important components arrive on time and helps prevent production delays caused by material shortages. Okay, so next for ACT is financial implications, which we have benefits and challenges. Okay, so I'll present to you about benefits first. Firstly, is lower maintenance costs, which is by using TPM and predictive maintenance, Proton can reduce unexpected machine breakdowns and spend less on emergency repairs. So next is lower defect and rework costs, which is visual SOPs and continuous training help production errors, so Proton spends less on repairs, inspections, and warranty claims. Third is higher productivity, which is a more efficient production process allows Proton to produce more vehicles within the same working hours, increasing revenue and profitability. Okay, so next is better resource utilization, which is better inventory control and improved production layout, reduce material waste, storage costs, and unnecessary labor. Next is challenges. Firstly, it's training costs, which is Proton needs to continuously invest in employee training and skill development to keep workers updated with new technologies and production methods. So next is technology investment, which is digital systems such as IoT sensors, predictive maintenance software, and real-time dashboards require a high initial investment. So lastly is facility expansion costs, which is as EV production grows, Proton may need to expand its factory, purchase new equipment or redesign production lines, which requires significant capital. So lastly for ACT, which is non-financial benefits. So firstly is improved product quality, which is better production processes reduce defects and improve the overall quality and reliability of Proton vehicles. Next is higher employee competency, which is continuous training helps employees gain new skills and become more confident in handling different production tasks. Third is better customer satisfaction and brand reputation, which is producing higher quality vehicles, increases customer trust and strengthens Proton's reputation in both local and international markets. And lastly is greater operational flexibility, which is a skilled workforce and efficient production system allow Proton to respond more quickly to changes in customer demand and new vehicle models.
In conclusion, the implementation of the PDCA cycle and lean manufacturing principles enables Proton Tanjung Malim to optimize efficiency, reduce waste, and enhance product quality through continuous performance monitoring and long-term improvements initiatives. Proton is now well positioned for the future. The steps towards digitalization not only strengthen current operation, but ensure Proton is ready to lead the expansion of electric vehicle EV, remaining highly competitive in the evolving global automotive industry. Thank you.